Next, I like to use a simple computing problem to show you this recursive thinking way. Okay, so we try to get used to this recursive thinking way. So let us calculate the factorial. It's so easy. We do not need to use recursion. Here you can, because we can easily, we use a for loop, we can calculate factorial. Why we need a recursion? It has its advantage. So here, I intentionally use the recursive thinking to work on the factorial. So we try to learn the basic steps when we using recursive algorithms. All right, the problem, our computing problem number 8. Given a non-negative integer n, find its factorial. N factorial. Okay, do the calculation. Very simple. All right, so here the reference reference in the textbook. So this chapter 4. All right. Method 1. The first one, non-recursive way, right? We don't need a recursion. Iterative way. So we just get a definition of factorial function. Okay. The product of the first n consecutive integers. The product. So you use a for loop. But when you define your factorial in this way, we have one special factorial we need to define here. So that is 0 factorial equals 1. That's our definition. 0 factorial equals 1. Can you understand that? Why 0 factorial equals 1? Can you imagine? Is there any reason that 0 factorial equals 1? Because based on tuition, it likes 0, right? 0. The most natural answer is 0. This definition has some base reason. It's not arbitrary. You can make arbitrary definition. No. This definition must be compatible with its general formula. Compatible. Okay? At this point, we cannot see it. But let me go to the recursive understanding. After that, then let's come back to this question. Okay? All right. This time, we couldn't see why it makes sense. Let's delay a little bit. All right. Now, method 1 implementation, easy. So I do not need to, talk about it. But method 2, we switch to recursive thinking. We intentionally, we use recursive thinking to understand this computing problem, simple computing problem. Okay, all right, so idea. So this is a general problem solving. Here, this actual recursion is a very general problem solving approach. Okay, so let's do that. Divide and conquer. Divide and conquer. And this divide conquer approach, it is so important. So in our module 2, we will spend another module to discuss this divide and conquer topic. Very important. Here we use a little bit, but in our module 2, we will spend much more time on divide and conquer. Okay, all right. The first general fact, that is, the problem is easier when the size is smaller. Okay, so this is a general principle. Okay, general principle. There could be some exception. There could be some exception. We're allowed to have So when we say general principle, most of the time it is correct, but we allow some exceptions. Yeah. We still allow some exceptions. So yeah. Exceptions, that means you can find some special examples. Smaller problem size could be harder than larger problem size. That could happen for certain exceptions. Yeah. But general principle is like this. Okay, all right. When you work on a problem of the current size, yeah, assume that a problem of a smaller size has been solved. Okay, yeah. So here, this recursion, when we work on problem of current size, we do not start from scratch. Okay, if you start from scratch, that means you start from very bottom. Okay, from very bottom, size 1, size 2, size 3, and going up to size n. So that's start from scratch, very bottom. Okay, that's not efficient. Okay, so we may like to go from the previous problem size. Yeah, so we can assume that a problem of smaller size has been solved. So we can just use that result directly. We do not need to use the smallest size cases. Okay, smallest size cases. We can start from some higher level. Okay, yeah, yeah, all right. But if you assume the problem of a smaller size has been solved from previous problem size to current problem size, there is still a gap, right? There is some gap. You need to bridge it. You need to bridge that gap. Okay? Yeah. You need to do some work to fill in that difference part. Yeah? Yeah. All right. So number 3, fix the gap through a recurrence relation. How to fix that gap? You need to discover a recursion formula. That formula is the way to fix that gap. There is a gap from old solution to the current solution. What is between them? Some formula representation you need to discover to fill in that gap. Then after you get that formula, recurrence, that formula, equation, yeah, equation, then you can implement that recurrence equation in a recursive function. Okay, yeah, so that's the general idea, general approach. Okay, yeah, all right. Now, let's use this factorial example to see this whole procedure. All right, so the formula, we know this formula. We have the original formula like this, okay, yeah. But now we intentionally want to write a recurrence version of this formula. This formula, it's not a recurrence formula, but we want to write a recurrence version for it. Yeah. So let us use a new function called f of n equals this n factorial. F of n. Okay. Yeah. The product of the first n positive consecutive integers, that's our f of n. Okay. All right. Then divide and conquer. Yeah. Divide and conquer. How do we divide? We draw a line to split this problem two parts. Okay, here the line we draw, we just cut off the last operand n. Last operand n. After we cut off that n, we need to calculate the result of the first n minus 1 consecutive positive integers. Based on our function definition, we have a function expression for this, the problem with smaller size. This time, the problem with size n minus 1, based on our function definition, it should be f of n minus 1. Okay? Yeah. But we can assume we have the answer of f of n minus 1. We assume we have it. Okay? So if we have f of n minus 1, how do we get f of n? There is a gap between them. Now when you fill in that gap, what is the gap? The gap is this operand n. We need to multiply another operand n. After this multiplication, the gap is fixed. Okay? Yeah. There is no gap. The gap is fixed. So we get a recurrence equation. Yeah. F of n equals f of n minus 1 times n. Recurrence. Yeah. Now you can write a recursive function to calculate f of n with this recurrence formula. Right? Yeah. Yeah. So implementation should be easy. Yeah. Okay. Yeah. But it's not necessary, right? For this simple question, it's not necessary. Yeah, I agree. This recursive implementation actually is the worst one than the direct for loop implementation because you use more resource. Okay, your stack is very deep, so you use more memory resource. It will be slower. Yeah. Yeah. So it's not recommended. Use recursive implementation for the simple problem. Usually, for relatively hard problems, then we are willing to use the recursive algorithm. For simple, we try to avoid recursive algorithm. Okay? For simple computing problems, we will try our best to avoid recursive algorithms because we want to save memory resource. But for hard, yes, we can take it. We know the problem is hard, so we are expected to spend more memory resource on it, so we can take it. Okay, so we are willing to spend that much cost. Okay, yeah. So, all right. Now, here I do not need to go to any details for the implementation for this question, but I want to explain our previous question, 0 factorial equals 1. Why is that? Now we are ready to explain that question. Why 0 factorial equals 1? Okay, yeah, we're ready. Now with the recurrence formula, we can understand why. Okay, with this formula, yeah, we know this formula must be correct, right? This formula is correct. Okay, so let's start with this formula, right? Yeah, to see, yeah, we can write in this way: f of n minus 1 equals f of n over n. So we write it in an equivalent form. So this is equivalent form with that previous, that older version. Yeah, also correct. Okay, also correct. Now, let us plug in n equals 1. Can we plug in n equals 1? Plug in both sides, n equals 1. The left-hand side, f of 0. The right-hand side, f of 1 over 1. F of 1 factorial, it's 1, right? 1 factorial is 1, no problem, no question here. 1 over 1 is 1, but f of 0 is that 0 factorial by definition. Yeah, f of 0 factorial. Now, based on this formula, it must be equal to 1. Okay, the formula tells us it cannot be anything else. It must be 1. That's the only choice for 0 factorial. Okay, yeah. Although it's hard to imagine why 0 factorial is 1, but based on this formula, it tells us we are forced to use this value 1 for 0 factorial. Otherwise, our general formula won't be correct. Okay? We want to make it compatible with our general formula. Okay, that's the explanation. 0 factorial. Okay, yeah. All right, yeah. Conclusion, yeah. It is an interesting way to solve problems. Different thinking, different approach, different method, sometimes could be useful, but here, this question is so easy, we cannot appreciate the power of recursion, right? Yeah. In this example, how can you appreciate the power of recursion? No, we couldn't. Yeah. So our next question, we really want to see some relatively hard computing problem for which we want to see the power of recursion.